Alright, so I wanted to follow up and make a video for you to show you how to model insulin and what you needed to do in order to use Jmol to identify the key components of insulin. But before I do that, I want to take a step back because I got a couple of questions from you guys over the weekend, and I want to clarify some of the concepts of what we're doing here. So in class on Tuesday, you learned how to use Jmol a little bit. You use a zinc finger. Zinc fingers aren't tied directly to insulin or CFTR, but the idea was that you would learn how to use Jmol and start to feel a little bit more comfortable with it. And as you use it a little bit more and more, you get more and more comfortable with it, just like anything else. So the reason that we started with the zinc fingers, actually because it's a very simple structure. And so there are very few steps you have to take. Insulin's a little bit more complicated, and the reason that we use insulin as our second model before CFTR was so that you can learn a little bit more about what's going on with this molecule and why the structure of it's so important. And so we're using this as a practice set, as a model for CFTR, because when you get to CFTR, your final structure is going to look different than any from other teams, depending on what you want to tell about your molecule. So let me show you real quick what I've done. This is a model of insulin that I have been through really quickly. It didn't take me very long, but again, I have more practice than you to show this model. And this is what insulin looks like. And I've used different colors to indicate different things. Let me just point out a few key features here. What I've done is shown an alpha helix here in this light blue-gray color. I've got a beta sheet in this yellow color. And this tube really represents the NCC backbone of the protein, and each bend represents that central carbon in the NCC backbone. That central carbon is referred to as the alpha carbon. So this is the alpha carbon, and it's really important to remember that any term that we use in Jmol with alpha in it refers to this carbon, not an alpha helix. So this is an alpha, this is a helix, this is a sheet in this language, or a beta sheet, and there are two chains here. So there's one chain over here, this green chain, and then this other chain that has some light blue in this alpha helix, some darker blue, navy or royal blue, whatever you want to call that, and then this yellow. That's one single chain that goes up, wraps around in this spiral, and comes around over here. And I'm not completely done with this. There are a couple other things that I would want you to do, and I'm going to walk you through it. But what I'm asking you to do is really try to pay attention to what I'm trying to show you here, because you're going to have to model this with CFTR. So if you're looking at each one of these, let me actually show you, type in a couple codes here to show you what this whole structure would look like if we were to look at every molecule in this insulin molecule. If we looked at every atom, in this insulin molecule. So So this is really every, and there are a couple of floaters out here, which are, if you look at this is water, H2O. If you click on these, it tells you a little bit of information. They're associated with these chains, but if you're looking at this molecule, you can see lots of carbons, lots of oxygens, a few nitrogens in the R groups. And that's what I've decided to show you in each of these. But when I undo that into the backbone, you can see these secondary structures like an alpha helix or beta sheets. And that's really important to understand, that when you remove some of these things, you make things more evident, other things more evident. I've decided to turn on the R groups, or the side chains of a few of these, and if you notice that, and if you know, maybe you know this yellow is referring to a sulfur atom. If I hover over this or click it, it's telling me that it's cysteine number 7 on chain A. This is cysteine 7 on chain B, and they are interacting. And And what's really unique about cysteine, even though, I'm going to make a couple notes here, that cysteine is made out of 2 atoms. It's 1 carbon and 1 sulfur. Sulfur likes to make disulfide bridges, which is really kind of cool because if you think about this, we've got an A chain and a B chain in here. And remember that when we did our activity in class, the order of the gene, the order of the mRNA, excuse me, I just hit the microphone, the mRNA sequence had a signal peptide. I'm typing into the right side over here of the screen. The signal peptide, followed by the B chain, followed by the what was called the C peptide, and then the A chain. And what's kind of interesting, remember, if the signal peptide is what's largely hydrophobic, and therefore it finds its way into the lumen, or excuse me, not even the lumen, the inner membrane space. So between the fatty acid tails of the double phospholipid bilayer of the endoplasmic reticulum, finds a nice home there, so it allows the rest of the protein to be made there at the rough ER. The B chain comes out, there's this connector called the C peptide, and then the A chain. And the B chain and the A chain fold together into this nice structure that we see here, and there was a C peptide that connected it all together, but we don't see that anymore. And part of the reason that the C peptide was there at all was to hold the A and the B in relatively close position to each other so they could fold nicely together like this. And you can see right here in a disulfide bond, there is a nice connection between the A chain and the B chain. There's another one right here, and one more down here. So there are 3 connections. So we're going to be actually showcasing 6 cysteines that are forming these disulfide bonds. And this file, as is printable, but the color is not going to print out. And so it's important that you color code this the way you want. And if you make a mistake, you can change it. Because once you print this out, you're going to be painting it for certain structures, like appropriate colors for the side chains, for secondary structures like alpha helices and beta sheets, so that it's evident to somebody else who may not know proteins as well what exactly is going on, and you can show them these trends in your structures, and you can also convey that to someone who studies proteins every day of their life. So we're going to be walking through that. So that's enough of the intro. I see I've talked for almost 8 minutes. Let's get going. I'm going to clear my screen here and walk you to, let me minimize all this. So what I'm at now is, well, let me show you how I got here. So if you go to pdb.org, you get redirected to this longer website. And what you want to do is click on Molecule of the Month. And just interestingly, right now it's the Zika virus. So if you want to read more about that, you're absolutely welcome to. But I'm going to search by title for insulin. And so type on, click on I for insulin. Click on insulin, and there's a lot to read here. I highly recommend that you read it. This is the kind of story that you need to be able to tell with CFTR. This is for insulin, obviously, but you're going to tell a story of how CFTR works. I'm scrolling down until I find 1TRZ. That's the entry I'm going to look for. Alternatively, you could search for 1TRZ. Here's that file. Lots and lots of information. Here's the primary source. It was published in 1994 by these 2 scientists, and their data was uploaded here. They got it out of humans. It's classified as a hormone. We already know that. They got the data through X-ray diffraction, probably from a crystal. And if we scroll down, there are several different things here. So insulin is modeled in chains A and C and B and D. And we've got some other things that we may not care so much about in our model. The data is there, and there's lots of data in the file, but we may not need to show or want to show all of it. And that's really important for you to determine what is important to show and what's important to hide. So I'm going to go ahead and download the file. I'm going to click on Download Files and go to PDB format. I'm downloading the file down here. I'm going to look at it in the folder. And what I've done is actually on my desktop, I'm going to hit Control Control C, I go to my desktop. What I've done on my desktop, and you can put this anywhere you like, is created a new folder called Insulin. And this is where I'd want to hit Control V and paste it in. I already have a file there, so that's the one I'm going to open, and that's a PDB file. Eventually what we'll be doing is converting it into a JPEG file. You might know that as a picture file, but that picture file, Jmol will store X, Y, and Z data points in, so I could actually import this back into Jmol and spin it around and manipulate it again as I like, but only if it's in the same folder as the original PDB file. So it's important that you make a folder and store all of this together, and then in Jmol save often. So if you've downloaded Jmol from the Google Classroom link, open it up. I'm going to open up my PDB file, and I get this. All right, so it doesn't look like my product very well. And so what I'm going to do is make this a little bit clearer to me. I don't like this this is called the cartoon format. I don't like it. I don't care for this, and it's not easily printable for us. But what's important to note here is that these pink ribbons with the arrows are alpha helices. I think you can see that. The yellow arrows represent beta chains. So you can see that, in fact, what's kind of interesting is we have 1, 2, 3 alpha helices, and well, we have 1, 2, 3, 4, 5, 6 alpha helices and 2 beta sheets. But if you look at this, and maybe you can see it, this actually double. There are 2 sets of things in here. Everything's in double. So let me clear this up a little bit. And I want you to do the same thing. And what I'm going to do is make this backbone 2.1, which is the size format backbone you're going to need for your printable CFTR file. I will give you that file later, and very soon you'll get that file. I'm also going to turn cartoon off, which is underlying all of this. I just want to take that data out, and I want to restrict some of that data. I've got these water molecules, say H2O, hanging out that I don't care for. And if I tried printing those, I'd get little, just tiny balls, circles or spheres sitting in my 3D printer and wasting a lot of energy and material. So I'm going to restrict to chain A or chain B. Remember, this is Boolean. So now what I've got is 2 different chains here. And I still got water molecules associated with these files. So what I'm going to do is say restrict chain A or chain B and alpha. That didn't. I think that's my syntax. So here's a key. Hit the up arrow, and it goes back through your previous commands. I think this will work. Yeah. All right. So it got rid of everything but my alpha carbons. And to make this a little clearer, maybe you don't know where one ends and one starts. So what I want you to do also is to select, let's say, chain A, and color it whatever color you want to color. This I don't care about, maybe except for yellow and red. So I'm going to color this orange. So it did this whole thing in orange here. And then I'm going to select chain B and color blue. All right. So those are my 2 colors now. And so what I want to do is find the first amino acid in each chain. So I'm going to click on that. Well, I want to. Okay. So this is amino acid number 1 right here, and this, if I can get it, is 30, right? So here's 1, here's 30. They're both on the B chain. And if I'm thinking about my NCC backbone, what I want to do is make sure I color these appropriately. So if I select chain B and 1, amino acid number 1, I want to color, well, it says 11 atoms selected because it's probably, if it's phenylalanine, that's actually one of the bigger amino acids with the side chain. But I'm only looking at the alpha carbon, so it doesn't really matter. But what I could say is and alpha. So I've got just the alpha carbon or the central carbon. And I'm going to color that. I'm going to make it light blue since it's already blue. And then I want to select, oops, let's go back up my commands. It's going to be amino acid number 30 on the B chain. And I want to color that red, just like we put those caps on your tubers when we were modeling this. And we do the same thing for the orange ones. So that's number 21, and this is number 1. So I know there are 21 amino acids in this orange chain. So we're going to select chain A this time, and 1 in alpha. Color that blue for the nitrogen on the NCC backbone. Select B, sorry, A and 23. Why is that wrong? Oh, 21. Sorry. There is no 23. Color red. Alright, so I've got my end caps on these tubers. And that's a great start. But I also want to color my alpha helices and beta sheets. So if I want to color my alpha helices, what our general rule, I'm going to have you do this general rule. We're going to type in select helix, and let's just do on one chain. On chain A, let's do and the alpha carbon, color red. And let's see if there was a beta sheet on this. So instead of helix, we turn that into sheet, and we don't get anything. So what we do is chain B has that, and we'll color it yellow. And there it is. Okay? So we've got our secondary structures here, but we need to highlight why we have some of and we could also, you can color this alpha helix. Actually, I'm going to let you, yes, I want you to color this alpha helix red on the B chain. So I'm expecting to see that in your file. But we need to highlight some of the side chains here. And so I'm going to write out the list here that you should have. Now, this is something that you will have to do some research on, and I will provide you some resources to help you with this. But there are two interacting chains here for its quaternary structure. So on the B chain, there are 2 amino acids that you need to show. Cysteine number 7 and cysteine number 19. As well as on the A chain, you need cysteine 6, cysteine 7, cysteine 11, and cysteine 20. And that should sound very familiar to you when you were doing the folding. These were the amino acids that you were showing that interacted, and these are the ones you were supposed to connect on that map, on the gene map. And so what you should connect is cysteine 7 of the B chain with cysteine 7 of the A chain. Those actually create one of the disulfide bonds that I showed you at the beginning. Cysteine 19 of the B chain interacts with cysteine 20 of the A chain, and cysteine 6 of the A chain interacts with cysteine 11 of the A chain. And so what we need to do is highlight those. So I'm going to show you how to do one set, and you're going to have to do the others. Okay, so what I'm going to do is show you how to select them. So let's start with the beta chain cysteine 7. Okay, so what I'm going to do is say select chain B and cysteine 7 and side chain. And so let me go over the logic of what this means. So think of this as a Venn diagram. I'm narrowing down. So the thing that I'm selecting is the in the middle of the Venn diagram of these three components. So I'm looking in chain B. I'm looking specifically at cysteine 7, not cysteine 7 on chain A. It has to be on chain B, and just the side chain of cysteine 7, so not the NCC backbone. And so once I've selected that, I should only have 2 atoms selected because it's just the side chain. I should say the cysteine side chain up here is made up of 2 atoms. And so if I hit enter, that's what I should get, and that's exactly what I got. But nothing changed in my model here. And so what I need to do is show them. I've just selected them. Remember, there's lots of data here, but unless I say I want to see it, it doesn't show. So I'm going to turn on the wireframe, and that's a must for your printable file. If you don't do that, your pieces aren't going to be connected. So if you turn on the wireframe to 1.0, we see, if you were watching, you see something pop up right here. It's sticking out right there. And I want to turn on the space fill to 1.5, and I get 2 spheres there. They're different sizes, and if I type in color CPK, I get this gray for carbon and the yellow for sulfur. And the CPK system is a standardized coloring system. This is required for your side chains so that we can see what those chemical properties of those atoms are and make predictions. So when I see this yellow sphere, I might expect a disulfide bond, and that disulfide bond is likely coming right over from the side. So that was cysteine 7. I told you this cysteine 7 interacted with this cysteine 7. So let's turn that one on. So I'm going to go back, just hit the up arrow until I get this command. It's the same cysteine number, but it's on the A chain. So I got 2 atoms again. I'm going to turn on my wireframe, my space fill, and my CPK, and there I go. And so I've got my disulfide bridge here. All right, so I'm expecting you to do the others in this list. And what I want you to do is save this and email it to me. No, I'd scratch that. I'm going to make a file in Google Classroom, a folder that I want you to post your file in. But know that you will be authentically assessed on this. So you want to make sure that you know how to do this. And if you don't, that you stay after school and get some help with this ASAP, because your CFTR protein is going to be a lot more complicated. So to save this file, you click on this picture. And in that same folder where you have the PDB file, you type in, what I want you to type in is your name, your first and last name, and the molecule, and version 1. And I hope that you continuously save this type of file, because that's really important that you do that. The other thing that I want you to do is right-click in the file, go to File, Export as an X3D 3D model. And I want you to put it in that same folder. So I have to find my insulin folder. I'm going to save it as an X3D file, which you have no idea what that is, but this is a file, or you may not. This is a file that I can then work with to export it out to our 3D printer. Hit save. Gave me an OK down here that it's saved as that file. And what I would highly recommend is that you copy and paste this into a Word document, because this stuff in the console does not save. And again, to get that console, you have to go File, Console. I forgot to show you that at the beginning, but that would open up your console. Okay? I think that's long enough.